Hello, everyone. Thanks so much for being here. So I'm going to talk about the predictive role of machine learning models. So the previous 2 days, we heard a lot about representational role of machine learning models, whether they represent, and if so, do they represent like toy models or do they represent in a different way? We also talked a lot about black box nature of machine learning models, how we have to kind of like resolve this sort of problem. But a question that is very much dear to my heart as an applied mathematician who became a philosopher of science was kind of what role this mathematical plays in the world, how are they being applied to the world. So I used to do operations research, working in with airline companies, like trying to design algorithmic systems for very mundane problems like crew scheduling. But basically, you put these algorithmic systems in the wild, and then you change something in the world. Now, if you kind of take that practice and kind of like apply it to many different realms, you feel like you are taking these mathematical models, computational models, machine learning models more specifically for this talk, and then you do something in the real world. You transform the world, you revolutionize the world, something. And so the kind of question that I have and the kind of like research project is like how we can make this transformative kind of relation a little bit like more philosophically robust and interesting. Okay, so how do mathematical models apply to the world? I would say like every scientist, mathematician, philosophers agree that they kind of like try to represent some specific kind of phenomena, many different ways, many different kinds of mathematical models. And from the time of Plato until today, every mathematician, philosopher of science had said something about this. I just put the book of Chris Peacock as just one example, but there are many, many other people who have written and published on this. And so here the puzzle, the representational puzzle is that you have these mathematical structures, you know so much mathematical theories in many mathematical domains. And then there are some kind of like physical stuff out there and like how in vitro what these mathematical models represent stuff in the real world. And so basically, recent philosophers have tried to capture this representational role in terms of similarity mapping. So basically, the kind of idea is that you find some similarities between mathematical structures and physical structures. And like, that's where all the whole like magic is gonna happen. 2 examples, again, like so many examples. One is from this kind of like very cool paper and computational biology published in 2017, where this computer, a couple of actually interdisciplinary group of scientists composed of pure mathematicians, biologists, and people who were doing computational social sciences got together and wanted to study this phenomena of how we have to think about the formation of color patterns on the skin of this specific lizard. And so that was the question they asked. And the reason they asked this question in 2017 was that until then, people were just using like Turing equation models, something like Turing equation models, to understand, to basically not understand, to represent the formation of the dynamics of color patterns on animal skins. Now, what these computer scientists and this interdisciplinary group of researchers found, they just found that actually you can model, like represent this phenomena in terms of a set of cellular automaton models. And for them, it was so interesting that these cellular automaton models are very different from these differential equation models. And the question they asked is like, how do these representational models relate to one another? But basically, whether you represent this pattern formation by kind of differential equations or cellular automaton models that are an example of computational models, what you are really doing, you're trying to represent something in the real world. Here, skin color pattern formation. Like a lot of very interesting examples, Lena mentioned yesterday, Emily, Katie, etc. Like there are cases where you're using some sophisticated version of mathematical computational models to, again, represent something in the real world. You want to represent how the brain is functioning. This is an image from a paper where scientists were trying to understand how the brain functions or basically how we can represent different brain states when people get psychedelics. So basically, again, another way in which you're like using some mathematical machinery in order to represent brain states, and a lot of other examples. Okay, so this is a very interesting philosophical question, how these machine learning models like represent. And we heard yesterday from Emily one account of how we have to make sense of this kind of like representation. Now, the question of explanation is very interesting in relation to the machine learning models, because over the past couple of years, we haven't asked the question of how machine learnings explain things in the real world. We have asked more the question of how we have to make this black box model explainable. But this question of explainability or explanation questions about machine learning models have been present. Before the machine learning kind of like, let's say, deep learning neural network kind of like age becoming so popular, there's been a lot of work on explanatory roles of machine learning models. And the main question is like, do machine learning models explain in a very unique way? Or is it that just they represent things and then we use this representation in order to explain some phenomena? It's a very interesting kind of collection of papers, like Mark Lang's papers, like in this volume, again, loads of many other papers. And then basically here the thought is that, is it the case that you can use some mathematical phenomena, like mathematical results, mathematical theorems, in order to explain something like in the real world? So there's an example here from Parker's optimality model. And here in this example, like in the lower side of the slide, like Parker wanted to explain how, like a specific empirical phenomena that she and her colleagues observed. And basically, there are like two different kinds of variables. The one is like the time that is spent for copulation by young flies, and then the other kind of parameter is, or the other variable is like the proportion of the eggs fertilized. And then the kind of investigation, the kind of scientific question that they ask is like, why there is this like very specific kind of like optimal point at which the down flies kind of the time spent and the propagation of the eggs fertilized, like why we observe that empirically. Because down flies can also mate with other kind of down flies, and so the question is like, why there is this point of like specific trade-off. So they explain that in relation to some like optimization kind of results. This is one example in which you use some specific phenomena from optimization that speaks very nicely to a mathematical representation of a specific phenomena, and then you say, well, from optimization theory we know X, that explains something in the empirical phenomenon. One other example, not really scientific, but also like a very popular example among philosophers, is like when we have these 7 bridges of Königsberg, and then we want to kind of explain why no one ever can cross these bridges exactly once, and you are going to kind of like map this problem onto a graph theoretical kind of structure, and then you know some mathematical properties about Euler path, and then you see those mathematical properties are not present here, and so therefore it's impossible in practice. It's a kind of a possibly explanation. It's again impossible in practice to cross these bridges exactly once. Okay, so that's been another kind of role for applied mathematics that people have been trying to really understand and explore. And when we put these two kinds of explorations together, again, there are loads of philosophers, mathematicians have been written about this. So I'm biased. I picked this this kind of collection of like work in this specific account because I think this account like brings in these different roles all together. Basically, the account that we have from Ottavio Bueno and Stephen French, and I tried to add something to the account in a 2021 paper, is that look, you have this like representation of empirical phenomena, E1, you kind of map that into a specific mathematical model, and then sometimes you draw some mathematical results, consequences from that model, and then you interpret that back to the empirical phenomena. And that is how we have to think about applied mathematics. the empirical phenomena E2 can be similar to E1 or can be different. But it's this empirical phenomena out there, and then we want to kind of explain something or represent something. So with this account, you can both capture representational role of mathematics and explanatory role of mathematics. Okay, so then if as an applied mathematician or philosopher of applied math, you want to know what and how mathematics is connected to the world. According to this example, you feel like, okay, mathematics represents aspects of the world or helps us to explain or understand things in the world. Okay, so I call this concept of applied mathematics reflective because it's an example in which you feel like you get some description of empirical phenomena. When that's done, then you try to explain or represent something about that phenomenon by applied mathematics. But there is this other body of literature that has not been, I would say, central to a big chunk of discussions about the philosophy of applied mathematics, where different kinds of philosophers and sociologists from different disciplines try to bring attention to this performative role of first philosophy of language, linguistic utterances by Austin, but then sociology of economics, like the performative role of economic models, financial models. In the book in the middle, Donald Mackenzie, who's my colleague at the University of Edinburgh, and basically he's the student of this Edinburgh School for the Social Construction of Knowledge, has done a couple of very, very interesting studies showing how, basically claiming how financial models shape the markets. So basically the ramification of that for science of economics is that it's not the case that like economics just studies financial markets or something. Economists actually use models to shape that market. And so that is a very interesting phenomenon. And many other people have been trying to get at this conception of performativity, maybe with different languages. So another work is this great book by Harry Morgan, where again, she tries to kind of like look into the practice of economics and basically saying that the economic models just do things. And when economic models do things, then it means that they become normatively salient. So it's not that they're just representing, they help us to represent or explain things, they are more than that. Now, huge discussion in philosophy of economics about whether Austin's conception of performativity is the conception of performativity that Mackenzie and other sociologists of economists talk about. Like Maki, for example, very much kind of like goes against this idea that we can kind of group these ideas all together and just like say that performativity of economic models is similar to performativity of utterances, linguistic utterances. But then one of my very favorite kind of authors in this space, Nicholas Priest, I think he has written a lot of work to kind of respond back to Maki and say, basically, if we interpret Austin in this specific way, and we have good reasons to do that interpretation, it seems like economic models kind of behave like these linguistic utterances. And so we can think about them in relation to speech activity. But I would say it's not necessary to kind of like say that if we definitely need to have Austin, it's necessary to have the account of Austin to make sense of performativity of economic models. You can just like say, okay, Austin is not relevant. There's this other conception of performativity. But just want to flag that there's a huge kind of like literature there. Okay, so then if we bring that kind of literature that has been discussed in specifically philosophy of economics to applied mathematics, the practice of applied mathematics more generally, it seems like we have this other role for applied mathematics that maybe philosophers of science should pay more attention to, and that is like a performative role of mathematical models. So in a paper that's forthcoming, I've argued that it's like predictive models in general, not just in economics, but in general, kind of give us this flavor of the performative role of mathematics. But the rest of the talk, I want to talk about performative predictive models. And I want to kind of connect the work to a specific, very interesting body of papers about performative prediction that has appeared in the literature since 2020. So this is like the main paper which kind of like triggered the discussion on performativity of mathematical models. But there are so many other papers you can after this paper. But if you look at the authors, basically it's just this group of people, many more, but you can find a lot of papers on this kind of work. And so in this paper, the authors kind of say, look, let me look into the practice of machine learning models. And so basically the question is like how machine learning models are making social predictions. So translating that to the philosophy of sciences, then that would be the question of like, how should we think about the performative or predictive role of machine learning models in social sciences? So that's how the kind of connection is made. And so these authors say, okay, like whenever you want to make a prediction with a machine learning model, it seems like we have sometimes this passive image of how machine learning models is doing the prediction according to a specific kind of way of talking about machine learning models. So you have this kind of like population that is represented as a fixed distribution D over data XY. And then the project is really to find a predictor like theta x or fx, whatever, to minimize the loss function on this D. And then you want that the expected loss of this predictor, like for supervised learning setting, to be equal to this risk. And then you want to minimize that kind of risk. And so they want to say, like in this, basically these authors claim that like in this language, in this way of talking about supervised learning, the notion of performativity just doesn't appear because it looks like we have some variables. We don't have any kind of causal language there. We have some sort of variables, and then we want to find relationships between an output or a predicted output and the data distribution, or more precisely, the kind of a sample that we've received from this data distribution. And so that's what really this is all about. But when we look into the examples in which these machine learning models come into the wild, so they're used in whatever kind of phenomena, for example, YouTube watch time prediction, it seems like these models predict, but at the same time that they predict, they also change something in the real world. Like that is a fact, that is what they want to bring attention to. And so, for example, simple example is like when you have like some users and some features about users and videos, and then you kind of like mix or make this like fixed distribution D over features X and the Y. The Y is like the watch time prediction. And then you want to have like the predicted watch time, like that is your predictor. And basically they say, which is true, that's the observation, that like this predictor kind of determines the screen ranking when it is applied in the real world. And so depending on what is shown to us as users, we are going to decide basically how much we watch that video or what would be the watch time. So the idea then is that when you put these models in practice, it is very interesting that there's this sort of causal relation, right, between the prediction and the empirical world. Okay, now, so this is what the computer scientists said, and now the question is what I'm going to add to that literature as a philosopher. So what I'm going to add to this literature is that computer scientists bring attention to a very important topic, performativity of machine learning models, and that's philosophically super interesting because we want to know, philosophers of applied math and science, how these models relate to the world. But the image, the notion of performativity that we get from the purely computer science perspective is very limited. In particular, again, I explained the next slide, they just talked about this a specific kind of machine learning performativity, which is called, I call it distributional performativity. And I want to add to that notion two other types of performativity that I call extrinsic and epistemic. And then I want to claim that actually this kind of topics or these types of performativity are all related to each other. And it's very important to get this like more comprehensive picture of performativity of machine learning models, because we want to mitigate that and we want to stop that in some scenarios. Okay. So the first, extrinsic performativity. So this kind of goes back to that, just very quickly going back to this image that I gave here. So that is the account of applied mathematics that I'm kind of like using. So extrinsic performativity is when you have like some empirical like you have some empirical phenomena, you quantify that, you build a data set, like, and then you kind of map that to a mathematical model. That's the representational kind of function, in the sense that you want the model to represent some patterns and find some patterns in the data. So it finds and it learns, but that's in virtue of that, it also finds some representational relationship to data. And then you kind of do this prediction, and then let's say y hat is the prediction you get from your predictor. And then in the case of like YouTube example, or another example I have here, that predictor, again, when these models are employed in the real world, is going to like change the empirical phenomena. So one example here is like you have a machine learning model that predicts how likely could a crime in a specific neighborhood, and then because of this predictive knowledge or this predictive information, law enforcement agencies allocate more resources to that specific area. So the increased police presence and surveillance can lead to more crime detections and arrests. So the idea that like it's not like this prediction that is normatively innocent, it's in the real world, actually it changes things in the real world. And again, just to clarify this, I'm not talking that there is this pure mathematical models that changes something in the real world. That is not the point. It's just there's applied mathematics, machine learning models applied in the world, and that system is changing something in the real world. Okay, so what are the necessary conditions for having this extrinsic performativity in the real world? So the first is that the model must be used, and then the second is like the word must move as a consequence. I'd be happy if you have more comments or directions to give on that. Just also another point to clarify here, there's been in the 1950s, again, in the whole economics finance literature, a lot of people try to make a connection or distinction between public and private predictions. So private predictions are predictions that, for example, imagine I'm a machine learning researcher, I use this model to predict something on my kind of computer. I'm not going to apply or deploy that in the real world. They call that private prediction. And public predictions are those predictions that are happening due to the kind of use of these models in the real world. I don't like this terminology, this public-private. It has its own problems. So I think the best way to kind of relabel that kind of definition that is coming from the economics literature is just to talk about like performative predictions versus passive predictions. Not sure if it's the best terminology, but I just want to say I'm putting aside the passive predictions, the predictions that scientists or other people do in kind of like in private kind of aside, right? So it's all about the cases of applied machine learning when you're using it in the real world. Okay, distribution of performativity is what actually these computer scientists very much talk about and develop various ways to kind of control that. That happens when you have this kind of like predictor giving a prediction, impacting something in the real world, that you collect that data and then you feed that back into the model, right? So here, the whole changes that has happened in the real world are translated into a second data set and fed back to the model, and then this process can like continue, especially for models like the models that are used, in like real time, like recommender systems like YouTube, Netflix, but also identification of many other like social phenomena, social media, etc. That's what a lot of social scientists are interested in thinking about. And so here, basically, a lot of this literature in machine learning wants to say, look, what happened here is that from D1, you get to D2. And so here, you're going to have like a distribution shift because the empirical work has changed. distribution shift, and how can we make sure that we can control this distribution shift. So that's like, and then there are a lot of like interesting optimization results and risk measures, etc. And so, yeah, the necessary conditions, the model must be actively used in a setting where its predictions have direct influence, and the outcomes of the model's predictions must be captured as new data and fed back into the model. And again, with the current machine learning models, you have a lot of these instances. And the third type that, again, I introduced here is when this prediction does not change something in the real world, but it changes some beliefs or knowledge states, and in virtue of that change in the belief or knowledge states, we act, or humans act in a way that something in the real world is changed. So one example is you have an influential machine learning model that predicts a particular cryptocurrency kind of surge, and then the investors kind of go by based on the knowledge of this prediction. The model doesn't change anything in the world, but we act on that knowledge, and that drives up the value based purely on that specific kind of prediction. That's another way that these machine learning models can perform things in the real world. Necessary conditions, the model's predictions must be accessible to a broader audience. We should put trust into the predictions of those models. And the audience must be willing to kind of adjust their behaviors or beliefs or decisions in accordance to that. Imagine this is like interesting, like what should we do about that? I was more interested in exploring this notion of performativity. I mean, one interesting thing about it was to just understand how machine learning models relate to the world. But another kind of question related to AI ethics that I've been working on over the past couple of years is like how we can use this notion of performativity or these different types of performativity in order to make a case for a variety of ways that we can control these systems to make more safe and responsible kind of machine learning systems. Okay, so extrinsic performativity, we want to, because that happens, that's the idea that like when you have these models employed in social settings, that's gonna happen. We need to design in the world mechanisms to resist or accept the extrinsic changes. Maybe in some settings, it's good actually for the model to perform something, but sometimes it's not good. Again, normatively loaded question, how we are gonna do it if there's a socio-technical kind of like solution. We need to seek for a socio-technical solution, meaning that just changing something in a model necessarily does not prevent this performativity to happen. The second kind of type, which is again what most of the people that in the performative optimization literature for machine learning models talk about, is like, let's think about different ways to improve the model responsiveness and adaptation through the adjustment or distributional shifts. Technical solution, you need to find ways to control that. And the last type of performativity, epistemic performativity, is like we need to find ways to kind of control that knowledge impact that we get or cognitive impact that we get from these predictions. And again, a huge socio-technical challenge. Yeah, and thank you so much for your attention.